Open Shortest Path First, or OSPF. OSPF is an industry standard, powerful routing protocol used in many networking environments in the world today. The word open means that it's an open standard. This is a great advantage to using OSPF because of vendor interoperability. You can mix Cisco routers with Nortel routers, HP routers and others, and be assured that routes will be exchanged between the different vendors. Shortest Path First, or SPF, also known as the Dijkstra's algorithm, named after the developer who published the algorithm in 1959, is used by OSPF to determine the shortest path or best route to a destination. So what we're going to cover is firstly an overview of OSPF. Then we look at the features of OSPF. I'd like to show you how to set up a network using a single OSPF area. I'm going to show you the importance of loopbacks and how they determine the router ID. We're going to look at quite a few configurations and setups in OSPF, including multiple area OSPF and authentication. OSPF once again is a link state routing protocol and will flood link state advertisements or LSAs throughout the network or area, describing firstly the links attached to a router, in other words the router interfaces, and the state of those links. The state meaning a description of an interface and its relationship to neighboring routers. Is the interface up or is the interface down? That description would include, for example, the IP address of the interface, the subnet mask, the type of network to which it is connected, and the routers that are connected to that network, and so forth. The collection of all of these link states forms the topological database or link state database. Routers form neighbor relationships by sending out hello messages using either multicast address 224.0.0.5 or unicasts. LSAs once again are flooded throughout the network or area, and the link state database is created from these link state advertisements or LSAs. OSPF once again uses the shortest path first algorithm or Dijkstra's algorithm to determine the best path to each destination. Now there's a bit of debate about this. Engineers will often discuss where in the OSI model various protocols reside. OSPF resides directly on top of IP. OSPF does not use TCP or UDP for transporting of updates and information. It resides directly on top of IP. OSPF is referenced in the IP header with protocol ID 89. TCP is referenced with protocol ID 6 and UDP protocol ID 17, and thus some would debate that OSPF resides at layer 4. For this course, however, we're going to say that OSPF resides at layer 3, directly on top of IP, also at layer 3. For a lot of us in the real world, this isn't a major concern, but maybe from a theoretical point of view. Here's a Wireshark capture showing various OSPF packets. So as an example, this first one is from a router with an IP address of 10.1.1.1 going to the well-known multicast address for OSPF 224.0.0.5. So that's the address used by OSPF for hellos on, for instance, an Ethernet segment. And you can see in the output here at layer 2 we've got the source MAC address of the router sending information to an IP version 4 multicast address, in this case the well-known multicast address for OSPF. At layer 2, the ether type is 0800 in hexadecimal, in other words referencing IP. At layer 3, we've got the source IP address once again of 10.1.1.1 and destination of 224.0.0.5. You can see this is an IP version 4 packet, and you can see here the protocol ID is OSPF, in hexadecimal referenced as 0x59. Using our Windows calculator, we can set it to use hexadecimal, set the value to 59, and then change it to decimal, and you can see the protocol ID is 89. So at layer 3, OSPF is referenced with protocol ID 89. The source once again is 10.1.1.1. Destination is the multicast address for OSPF. Residing directly on top of IP is OSPF. So notice we have Ethernet, IP, OSPF. OSPF does not use TCP or UDP as a transport. It uses IP. You can see the OSPF header. It's version 2 of OSPF. You can see that this is a hello packet, in other words type 1. You can see it's for area 0. OSPF areas can be referenced either as single decimal numbers like 0 or in dotted IP decimal notation as in 0.0.0.0. It's like saying tomato or tomato. It's the same thing. You can see the source is 10.1.1.1. You can see it's a hello packet. There's information like the network mask, the hello interval, the router priority, the router dead interval, who the designated router is, who the backup designated router is, who the active neighbor is, and so forth. We're going to cover a lot of this information in the upcoming slides. The important thing to notice once again is that OSPF resides directly on top of IP. If we look at the next message, where router 10.1.1.2 is sending a database description to router 10.1.1.1, you'll see once again that there is no TCP or UDP. OSPF is referenced with protocol ID 89 in an IP version 4 header. OSPF for this course resides at layer 3, but as mentioned, there's a bit of debate about exactly where it resides. A router sends link state advertisements to advertise the state of a link immediately when the state changes or periodically. By default, every 30 minutes, the databases will be synchronized with the state of the links. OSPF routers form neighbor relationships, and the list of neighbors is stored in the adjacency table or OSPF neighbor table. So typing the command show IP OSPF neighbors will show you adjacent neighbors. OSPF uses multicast addresses 224.0.0.5 and 224.0.0.6, which are link local multicasts. In other words, those multicasts cannot hop across a router. The routers have to be directly connected. OSPF will store all routes learnt in the OSPF topology database or link state database. The link state database contains all routers and attached links in the area or network. All OSPF routers in the same area share the same database. Best routes are then put into the routing table, also known as the forwarding table. There are various packet types used in OSPF. The first type is a hello packet, which is used firstly to dynamically discover neighbors, and secondly to form neighbor relationships and maintain those neighbor relationships. There are some default intervals for hellos. On broadcast multimedia segments such as Ethernet, the interval is 10 seconds. The second default interval is 30 seconds, which is used on non-broadcast segments such as serial links and MBMA, non-broadcast multi-access environments such as frame relay. OSPF has what's called a dead interval or dead timer, which is 4 times the hello interval by default. If you change the hello interval, OSPF will automatically change the dead interval to a value 4 times the hello interval on a specific interface. So hellos are used to discover neighbors, and if a hello is not received within the dead interval, the neighbor relationship is torn down because it's deemed that the neighbor is no longer available. The second type of packet is what's called a database description, written as DD or DBD, which is used to exchange brief versions of each link state advertisement. OSPF is a link state routing protocol. Routers exchange information about the state of links through link state advertisements. When an initial relationship is formed between two OSPF routers, they will exchange database descriptions, giving each other an overview of what the database contains. If parts of the database are missing on one router, it will send a link state request requesting full LSA information from the neighboring router. The neighboring router will send what's called a link state update which is a packet that contains link state advertisements and, as mentioned, is typically sent in response to a link state request. This contains detailed information about the link state database, rather than just an overview of it, which was contained in the database description. Link state acknowledgements acknowledge or confirm receipt of a link state update message.